In this video, we're going to be doing a Unit 5 rotations MCQ practice. So for our first question, we're going to start off with a solid disc rolls without slipping down a ramp. It starts from rest and has a constant acceleration. After 4 seconds, its center has a speed of 8 meters per second, and the disc has a radius of 0.5 meters. What is the angular displacement during this time? So what do we have here? We have that it starts from rest, so the initial velocity is equal to 0. We also have the final linear speed, which is going to be equal to 8.0 meters per second. Our time is equal to 4.0 seconds, and our radius is equal to 0.5 meters. So because we have constant acceleration, we can use archaic equations, which means that we can use the linear distance traveled by the center. So when you have constant acceleration, you can use x is equal to v average times your t. So you can rearrange this and you have v average is equal to your v initial plus your vf, because that's what an average is, divided by 2. If we're looking at specifically this part of the equation here. Now, all we have to do is just plug this in with our v initial and our vf that we were given in our problem, which was 0 plus 8.0 to 4.0 meters per second. Now, you just are going to sub that back in, and you have 4.0 times 4.0, which is equal to 16m. Now, we are going to use our rolling without slipping condition, because we have rolling without slipping in the scenario that was described. So you have x is equal to r times theta. So if you rearrange this, you can solve for theta. That's going to divide both sides by r. Theta is equal to x over r. So now theta is equal to, what is our x here? So we just found our x over here from this problem. We have x is equal to 16m. So we're going to sub in 16m here. And our r, we have our r from over here that was given in the problem, is equal to 0.5 meters. So that is going to give you, we'll remove these units. So this is going to give you, that was in green, and this is in orange. This is going to give you 32 rad, because angles are measured in radians. So now let's do another problem. Let's do a solid cylinder of mass 3.0 kilograms and radius 0.2 meters rests on a horizontal surface. A horizontal force of 6.0 newtons is applied by a string that is wrapped around the top of the cylinder, causing it to roll without slipping. On the top. So we had to find the acceleration of the center of mass. So it's being pulled horizontally to the right. This is going to be the direction of our acceleration. And we are rolling without slipping. We want the acceleration, the linear acceleration of that center of mass. So we need to determine the friction's direction. So whenever you have friction, friction is going to oppose motion. And because this pull is going to pull the cylinder this to the right, you are going to be turning your cylinder clockwise, and clockwise is equal to a negative torque. So this is going to cause negative torque. That would make the bottom point try to move left relative to the center, which means the relative to the ground, the contact point is going to slip left. So relative to the ground, your contact point tends to slip left if translation is not enough. we also know that Fs, your static friction, is going to oppose the tendency. So that means your friction is going to be to the right. We'll label this with this. So now if our force, this is our force, and also our frictional static is to the right, that means that would both of them produce opposite torques? Well, the force at the top is going to give you clockwise torque, and the force at the bottom is going to give you counterclockwise torque. So up here, you're going to, let's actually assign these different colors. That force is going to give you a torque that is encouraging you to go to the left, the blue. Let's change the color, or actually no. And then our static friction is going to cause a torque that is going to make you want to go positive counterclockwise, which is a positive torque. So friction at the bottom is counterclockwise, and our force at the top is clockwise. And this makes sense because our friction is going to reduce the rotational effect somewhat while still increasing our translation, which is usual. So that's why our F is going to be to the right, and our FS is also going to be to the right. So now we are going to use Newton's second law for translation. So summation of forces in the x direction is equal to ma. So we have a positive F and a positive FFS is equal to mass times acceleration. Now we're going to use Newton's second law for rotation. So the torque from the pulling force at the top is going to be clockwise. So the torque from the force is equal to the force times the radius. And then we can label this as clockwise. And then the torque from the frictional force is going to be negative frictional force times radius, because this is going to be counterclockwise. So it's negative in our sign convention. So if we take the summation of our forces, our torques, because this is rotational, we're going to have FR minus FSR is equal to I times alpha. So because we have a solid cylinder, we have I is equal to the 1/2 of the mass times the radius squared. So that's going to be FR minus FS. That's equal to 1/2 mr squared times alpha, because you are just going to substitute in this I here. So that was that 1/2 mr squared right there. And then now you're going to use the rolling without slipping. And that relationship is angular, or your linear acceleration is equal to your angular acceleration times your radius. So then if you divide both sides by r, you get that alpha is equal to the linear acceleration divided by the radius. Now you're going to substitute alpha into your equation up here. So if you do that, we can put this over here so we have more room. And you're going to get that FR minus FFS is equal to 1/2 mr squared a over r. So then one of these r's cancel out. So you're left with f r minus FFS is equal to 1/2 mRA. After this, we can divide both sides by r. We also had an r here, but I forgot that. So there's actually an r here. These actually have an r. So if you divide those r's are going to cancel out, and you're going to have f minus f is equal to 1/2 mass times your acceleration. So that means that from translational motion, you have f plus f is equal to ma. And then from rotational, you have f minus f is equal to 1/2 ma. Now, we're going to look at holistically, totally. We can add that. We can add your translational plus your rotational. So that means you have f plus f minus FFS is equal to ma plus 1/2 ma, because you also have that a is equal to, here you can rearrange this to a is equal to, if you divide this by m and you multiply by 2 over m, you have that m, you canceled out those, a is equal to 1/2 m. Actually, not from there, that would not be a good point to just get a. Here we know that if you have ma, you have that f minus f is equal to 1/2 ma. Just leave that there. So you have 2f is equal to 3 over 2 ma, so you can multiply both sides by 2. Now, in doing so, you get 4f is equal to 3 ma. So a is equal to 4f over 3m. Now you can just sub in. So you have f is equal to 6.0 newtons, m is equal to 3.0 kilograms, a is equal to 4 times 6.0 over 3 times 3.0. That's equal to 2.67 meters per second squared. Now, we can solve the rest of our problems as well. So, a wheel starts from rest and rotates with constant angular acceleration. After rotating through 8 pi radians, its angular speed is 4 rad per second. What is the angular acceleration? So you have to use the right rotational kinematics equation, which is that omega f squared is equal to omega initial squared plus 2 times alpha, the change in your angle, theta. So we have some things we can write down. So omega initial is equal to 0. Omega f is equal to 4 rad per second. Change in theta is 8 pi rad. So now we have 4 squared is equal to 0 plus 2 times alpha, 8 pi. So this is equal to 16. This is going to be 16 pi alpha and alpha is equal to 16 over 16 pi. So this is going to be 1 over pi, which is approximately 0.318 rad per second squared. So that's our answer. For this question, your answer was 32 rad, but I didn't circle it. A force F is applied at the end of a pivot of end of a rod of length L that is making an angle theta with the rod. What is true about the torque about the pivot? So torque is equal to RF sine of theta. R is the distance from pivot to the point of application. And theta is the angle between R and F. Here R is equal to L. So your answer would be, and also your force magnitude is equal to F. So your answer is FL sine of theta. 4 objects of equal mass and radius roll down an incline. You have a hoop, a solid cylinder, a solid sphere, a hollow sphere. Which has the greatest acceleration? So when you have rolling acceleration, your acceleration is equal to g sine of theta divided by 1 plus I over mr squared. So we are going to have the max A when your I over mr squared is smallest. That's because if you increase your denominator, then you are going to have a smaller overall fraction. Because if you have a number, a fixed number, and you keep dividing it by a larger number, it's just going to become a smaller and smaller number. So now let's compare the moments of inertia. So if you have a hoop, let's do this for each of the options. When you have a hoop, you're equal to mr squared. So that's going to be I over mr squared is equal to 1. And for a solid cylinder, you have I is equal to 1 over 2 mr squared. So that's I over mr squared is equal to 1/2. What about for a solid sphere? We know that its I is equal to 2 over 5 mr squared. So you have 2 over 5 mr squared over mr squared. So what is happening in each of these is you're just substituting in that I, and then you see that the mr squared cancels out. So you're left with this ratio of 2 over 5, which is how you're getting these answers. So this is 2 over 5. Now, what about a hollow sphere? You have inertia of 2 over 3 mr squared. So 2 over 3 mr squared over mr squared. Just like before, that cancels out, and you're left with the ratio of 2 over 3. So smallest I is going to mean the largest acceleration. So our smallest is going to be when you're at 2 over 5, which is going to be when you have this solid sphere. A horizontal beam of length L is pivoted at one end. A mass M hangs at the far end. A cable is attached at a distance L over 2 from the pivot at an angle theta. What is the tension T? So your answer we can get this from looking at the torque of the hanging mass. So it's going to have an mg downward. So the beam is horizontal. That means the angle here is going to be 90 degrees. So you're going to have T of the mass is equal to L times mg. And this is going to rotate clockwise. Now, what about the torque from the cable? So it's attached at L/2 with an angle theta relative to the beam. So that means that we know that if you have T perpendicular, that's equal to T sine of theta. So T of the cable tension is equal to T sine of theta. And that's going to be, tension is going to be, the torque from the tension is going, or no, this is actually tension that's perpendicular is equal to T sine of theta if you break it into components, aka the Ty. So the torque from the tension is equal to L/2 T sine of theta. And this is gonna act, it's pulling the beam counterclockwise. You're also going to have rotational equilibrium here, which states that the summation of your torque is equal to 0. So your equation is going to be your summation of your torque is equal to 0. Therefore, torque counterclockwise is equal to your torque clockwise. Your answer is going to be 2 mg over sine theta. For this question, our answer was 2.67 meters per second squared, but I didn't circle it. A rolling object starts from height h. What expression is its final speed? Well, we can use conservation of energy. Let's say that, for example, this was height h. How do we find this? We know that at the top, it's going to equal to ug. At the bottom, you have k, right? So we have conservation of energy. Since at the top we just have ug, and at the bottom we're going to have kinetic energy. So now we can use rolling without slipping. You can sub those in. So now you have 2 MGH. Then we want to solve for V squared. Divide both these by m. Then root. Your answer is 2gh 1 plus I over mr squared. A force F is applied tangentially at radius r, then at 2r. How does angular acceleration change? So it's going to double. The reason is and then you use a solid sphere is supported at both ends with a mass off center. Which condition must be true for the equilibrium? Your answer is C. Net force must equal 0 and net torque equals 0. You have to have summation of force equal to 0, summation of torque equal to 0. So for the beam to not rotate, both must be true. So a system can still have 0 net force. And for your last question, it's going to slip.